We can hear you.
Dr. Murthy, can you hear me?
I think he said he'd be back in like 2 or 3 minutes.
Okay, very good. So we are good. I started recording. I'll just pause for now, and then when everybody joins, I can restart.
One minute. Can you actually give me the sharing?
Started his career as a rocket scientist and founded one of the top data science institutes on Earth, the International School of Engineering. In addition to being a globally recognized academic, Dr. Murthy has been a senior mentor with Soothsayer Analytics for 5 years. In this capacity, he has architected and led numerous deep learning and artificial intelligence engagements and collaborated with such esteemed companies as Abercrombie & Fitch, Dun & Bradstreet, and Ford. This webinar will run about 40 minutes, and we'll save the last 20 minutes for Q&A. Please keep your mics muted till the end, at which point we'll answer any questions you have. Thank you.
Aya, there is a lot of echo, so please mute yourself. And now in the chat room, if someone can say whether they can still hear the echo. The echo for me is completely gone, but I just want to ensure that even the audio, okay, great. Thank you. So what I request is if we make audio enabled for the participants, we will see similar echo problems. So during the presentation, we'll keep the audio for everyone else mute. And as and when you have a question, I request you to type it in the chat box. And we will have a presentation for around 40-45 minutes. At the end, I will go through the chat box and try to answer as many questions as possible. If I am not able to answer all the questions in the stipulated time of 1 hour, we are recording the questions and the meeting. So we will be able to answer, we will actually answer each one of them and share the answers as a document with everyone else. Okay. So that's how let's conduct the program. A warm welcome to all of you. I know it's a lot more easier for me to join given it's pretty warm and nice here. I know you are having a fairly horrible weather there. So thanks even more for taking the time to join on such a day. I will try to, and I'll try my best to make it worthwhile, the whole 1 hour. What I want to present today is, to start with, I will give a few examples of some of the extraordinary achievements that deep learning made in the past 5 years. I will cover use cases from structured data, image, and text data, and show you why it is worth learning it now. And then I will talk about the fundamental differences between deep learning and statistics and machine learning. Statistics and machine learning have been there for the past 50 years. Deep learning is a past 10-year phenomena. While deep learning is a subset of stats and machine learning, there are some important differences that everyone should understand to be able to effectively implement deep learning. I'll talk about it. Very briefly, I will also touch upon the available tools and how they are simplifying data science. I'll not get technical in this 1 hour presentation. I'll just very briefly talk about how these things work to show you that it's easier than ever to build a team that can really build cool applications in deep learning. Towards the end, last 5-10 minutes, for those of you who are interested in learning further about this technology, I will talk about a couple of courses that we'll be offering in Detroit and Columbus. This entire presentation will take around 45 to 50 minutes. Post that, we will have a question answer session where, as I mentioned, I'll go through the chat room and try to answer as many questions as possible. Great. So the first example that I want to show is not something that is published or is not something that is not a research publication. This is something that one of our interns built in less than 2 days and with less than 20 lines of code. The reason I picked it as the first example showcase is to show you the power. This is a standard database called Movie Lens. It has 700 users rating 1,300 movies, and totally there are 100,000 reviews. So on average, each user rated around 100 to 200 movies. So we have around 100,000 reviews of 1,300 movies. The goal is a very standard data science problem where, looking at the movies and the ratings that a user gave, can we recommend a better movie to the client? And the current state of the art, it is published, current state of the art error is 0.9. So this state of the art paper is the outcome of the research conducted by a reputed group in machine learning, and around 4 or 5 years back they published it, and this is the best that is available. Yeah. And this undergrad intern worked on it for a couple of days. Important point to note is that he is not an expert in deep learning. I just request all the participants to stay on mute because there'll be a lot of noise. At the end, if you want to ask a question, you can unmute and ask, but otherwise you can use the chat room also. So the undergrad showed the results of 0.7 error. This is a 25% drop in error rate with less than 20 lines of code, or with very little expertise of the domain. This is like take the data and apply and get the result. So that is the kind of results that people are seeing. Excuse me. Can you guys go on? RMSE stands for the root mean square error. Please don't worry about the exact definition of the error. You can think of it as one way to measure the goodness. It is an error metric, and the state of the art is 0.9, and a intern project of 2 days yielded 0.7. And this is the kind of results that deep learning is producing nowadays. Very soon, you will have these deep learning teams of engineers who will be able to rewrite sort of the benchmarks of the models that you have been using for years in your organization. And you need to figure out how to use this power, channel it so that you can make best returns of the technology. This is another kind of problem done by a bunch of doctors, and this is published result in 2017 January. This model is built by practicing doctors, not data scientists. The goal is here to predict the probability of the fatality of a kid in an intensive care unit. Pico is pediatric intensive care unit. They want to essentially, when a kid joins at various time points, they have to figure out what is the probability that the kid will survive. The state of the art product, this is commercially available product, was giving 88% accuracy. And astonishingly, a group of doctors ran a base deep learning model, got a 93.4% accuracy on fatality rate. This is massive. This is massive, and it's not unheard of. These are the kind of things that is making deep learning extremely exciting for for practicing engineers. Now, what made deep learning really made the heads turn is its applications in image. And this happened in around 2011, what the case study that I'm going to show. And this is again going to be astonishingly interesting. There is a competition called ImageNet Large Scale Visual Recognition Challenge. The competition goes like this. Stanford and Princeton universities maintain around a few million photos like the ones that you are seeing on the screen. These are pretty difficult to tag even for a human. If you see the second row, there is an Egyptian cat, there is a Persian cat, there is a Siamese cat. So it's not that a human can get it accurately. Probably we know it's a cat, but to know what species of cat it is not very easy. The challenge goes like this. They will give you a million or more, I think around 10 million images that are tagged by expert human panels. You can use them to train your deep learning or any model, any model. Now they keep around 1,000 images with them. They will test your model on these images, and if the model is allowed to make 5 guesses. Even if one of these 5 guesses is right, they consider that the model got it right. So let's go chronologically to track the progress. We are in 2011. The expert human as measured was at 5% error. So out of 1,000 images that these guys kept, expert human got 950 right, and a less skilled human got 900 right, 5 and 10%. Machine in those days was at 30%. And they were estimating that the machine would take around 50 to 70 years to reach the level of human efficiency. And come 2012, the first deep learning model of computer vision was published, and the error dropped from 30 to 15.4. This is unheard of. Until then, year on year, they were seeing 0.5 or 1 or 2% improvement. And suddenly, in 1 year, they got the error almost to half its previous year's value. This is when people said, wow, this is cool. Something is either very right or very wrong in this thing. And people started working on the technology. Come 2013, the error further dropped to 11.2%. And less skilled human is at a threat. 2014, the second prize was at 7.3% error. And so less skilled human was beaten. And the first prize by Google was at 6.7%. And so an expert human now is at threat as far as vision accuracy is concerned. 2015 was a very important year in computer vision. Microsoft produced its deep learning algorithm, which gave 3.6% error, which is better than the expert human error. So in 2015, we started having computer systems powered by deep learning that were able to beat human accuracy routinely. So much so that nowadays, image classification is not even a task that people are interested in. They are looking at much more tougher problems like understanding the context of a video or an image, etc. So this is again, in 5 years, you can imagine the kind of growth that the field has seen and the number of new applications that it is leading to. Text took the longest to get revolutionized. But Google had published its latest translation engine. Now, if you focus on the first row, English to Spanish, the human accuracy. So the way they do it is they have a panel of human experts translate a text, and now they have individual human translators and machines to translate. and they count how many two-word phrases overlap between any given translation and expert panel translation. The fraction, and then it's converted to some scale between 0 and 6, the more the better. And a expert human translator was at 5.5, and when this paper was published, which was 2016, Google was able to achieve 5.428 in English to Spanish. And now we have systems that are getting extremely close to human. Probably 2-3 years from now, we will have systems that will surpass human, even in a complex human task like language translation. So whether you take structured data, like forecasting whether a kid will survive or die, or recommending a product to a customer, or a vision problem where you want to identify whether your product is developing a crack or is it good, or a text problem where you want to figure out is the sentiment of your customer positive or negative. The deep learning is revolutionizing, and the point that I want to make here is these are some of them, the later parts that I showed, are done by expert deep learning researchers who spent probably a year bettering the accuracy. But the initial ones that I showed are built by non-practitioners. When I say non-practitioners, non-practitioner of deep learning, they just took a library, ran it, and they got the result. So what is very exciting now, and probably a bit dangerous, is it is not only extremely efficient, it is extremely easy to get this efficiency. So hopefully that shows you why this is a very important field to study at this point. There are a couple of fun things that deep learning is doing. Again, that is probably unheard of before. Unfortunately, the audio is not playing when I tried on Skype. We will share this PowerPoint anyway with all the participants. So you can click on both of those audios to hear the PowerPoint. The left side is the original audio. It's Raindrops. It's a song created by a human composer. And the right side is generated again by a robo created by a student intern in less than a week. And you will see that while it learned the music, it did not copy it. It created its own, it produced its own notes, and which really sound nice. I wish I could play it, but Skype somehow doesn't enable it. So I will let it for you to listen to it after the presentation. Another very interesting fun application that deep learning developed in arts is this particular thing called neural style transfer. So this is, let's say, a photo of my son. This is not my son, but I'm saying there's a kid that I want to, I have a photograph of. But then there is this modern artist who is really famous, and I want him or her to paint my kid. But he is very expensive to hire. So the neural style transfer is a system where your deep learning machine actually learns the style of the artist and sort of figures out how to draw the photo, the content in the style that is asked by the user. And this photo that you see here is absolutely generated by an artificial system. This is not photoshopping. Nobody sat and changed the settings or ran filters. We just gave, again, this is a student project, we just gave a photo and the style, and the system figured out how to import that style and redo the picture. So whether it is a business problem or a fun art kind of a thing, this technology is doing things that even a few years back were considered unheard of or impossible. So it is important that everyone in the organization should learn, not just the fresh graduates or undergrads who we hire, who just picked up this technology from the school. The interesting thing is here is some of you, I'm assuming many of you have left college 10 years back, like me, and at that time there was no deep learning. The entire thing developed in the past 10 years. So for many of us, this is even unheard of, and this is changing the way we do our business. That is the reason why we are conducting this series. Given that motivation, now I want to talk about at a managerial level, what exactly is this deep learning or deep thinking and how it evolved. So let's understand how people actually learn from models to position deep learning and its power. So in 1900s, people started using statistics to actually analyze the data and get interesting reports that help them take better decisions. Typically, even today, this goes by the name business intelligence, BI, and organizations benefit enormously from it. But in a BI or a statistical problem, you know the logic that you want to implement, and you collect the data. Typically in statistics, you collect a few hundreds of records, not much more than that. And then you apply that logic using a statistical language on this data to measure the impact or understand the impact. So one example is a pharmaceutical industry, the scientist develops a medicine that reduces the blood pressure. So they want to actually figure out whether that claim is true or wrong. They collect a group of people, they assemble, they take their permissions, and now they create two exact looking tablets. One is the real medicine, one is the placebo. Administer it to these two different groups that are otherwise identical, and measure their blood pressure and see how it is changing, and validate whether the claim that this medicine reduces the blood pressure is valid or not. This is a typical statistical study. I know the logic, I collect the data, I apply my logic on the data using some fundamental statistical principles, and I validate whether it works or not. Right. So that is statistics, very prevalent and extremely useful. But starting 50s and more importantly starting 80s, people started collecting a lot more data, tens of thousands of records, hundreds of thousands of records. And they tried to solve problems about which they vaguely have an idea of the logic, or even sometimes they don't have an idea also. But what they have an idea is what aspects could be impacting the result. So let's say there is a insurance company that collects the medicine administration, the behavior of patients taking the drugs. And they may realize that, hey, some patients are dropping out after some time. By the way, this is a real world problem, an extremely important problem for insurance and pharma companies and government. Approximately 40 to 45% of the patients are found to be not adhering the prescription. But now they want to see why they are not adhering, or can we stop them from not adhering. Here, what I know is, hey, what could be impacting their medicine taking behavior? Maybe the age, maybe whether they are married or single, maybe their education background, maybe their financial status, etc., etc. I know vaguely some of these factors impact, and maybe I'm not confident, but maybe the gender of the doctor and might influence. I don't even know. Maybe I'm wrong, but I want to validate. Machine learning typically involves specifying these factors that I think will impact, and I'm not sure about the logic of how they impact, and I let the system develop the logic. So this is a huge step from statistics. If you look at statistics where I know the logic and I implement, machine learning or inferential statistics, statistical learning involves letting the system know just the parameters that are important, but letting it figure out what is the logic. And beautiful results were identified. Obviously, I am masking the result. We worked for a real company to solve this problem. So the results you see here are not right, but I'm just giving you a taste of what kind of patterns machine learning can get. Something like if the gender of the doctor and patient are different, the chances of patient not adhering are much higher. Now, that could be an action point for a hospital system on how to improve the adherence of the patient. So, till 2005, or till the dawn of this century, people were working on such problems where I know the factors, I don't know the logic. And in fact, the systems became so powerful, given a set of factors, the systems were able to extract better logic than a human expert. Now, since the dawn of this new millennium, a new kind of problems are tackled. And these perhaps are the most difficult for a computer, though they look trivial for a human. If I look at a person and recognize their face, what are the factors that I am collecting to recognize the face? And you know, human brain is extremely good at it. You meet a person 10 years after you leave the college, and you will be able to recollect in a few moments, say, you know what, I was sitting with that course with you in 2005. You know, are you Steve? And it's brilliant that human brain is doing. But the interesting thing is we don't have a clue of what factors we take into account. Do we look at the eyes? Do we look at the distance between the eyes, length of the nose, width of the mouth? What do we see? We don't know. But we are solving it with amazing accuracy. For a computer, it's even more difficult because what somehow we are seeing is a face. What computer sees is a bunch of numbers like this. Every image for it is a bunch of numbers, a lot of numbers like this. So deep learning solves this problem where now you have a lot more data. You are talking of millions of records, but you neither know the logic nor know the factors that you need to take. All you supply it is raw data that you are collecting. In case of image, it is the pixel values. In case of text, it is the word. In case of structured data, it could be the store ID that you assigned. The rawest form of data that you have collected, and the system will learn the factors that are impacting and then the logic that the factors are using to make the prediction. So if you see statistics, I know the logic, I know the factors. In machine learning, I know the factors that are impacting but not the logic. In deep learning, I don't know the factors, I don't know the logic. All I know is the raw form of data that I need to solve. And deep learning, that's why is revolutionary. Where there is no logic, it's able to solve the problem. Where there is logic, it is able to supplement and increase the accuracy further. And that's why it is breaking the benchmarks as we discussed in the motivation part. So what is deep learning? Essentially, because brain is solving these problems really well, scientists in 1950, around 1950, wanted to build a system that looked at least like a brain. So this, what you are seeing is a mathematical model of brain that was proposed in 1940s. The right-hand side is what you call a neuron. A neuron essentially is one of the fundamental components of human brain. Human brain has billions of them. The core of it is called nucleus, and there are some chemicals in that core, and they go through some electrochemical reaction whenever we feel something, and that signal is transmitted to through a tail-like structure called dendrite, and the dendrites of the other neurons are in proximity, and the signal just gets transmitted from one dendrite to the other, and then that dendrite generates a signal. Because of this signal, it transmits it to the next dendrite. So the brain actually has these billions of neurons. Each neuron does a very simple act. It just generates a signal. But the way they are connected, the way they transmit from one to the other leads to the kind of amazing creativity and intelligence that we are seeing in human brain, or for example, any animated brain. So people were saying, if I build a system like this, can I actually get the kind of intelligence that brains have? What you are seeing now is the brain model built in 1950s. This was called Perceptron. If you closely notice, there are neurons of the previous layer, neuron of the next layer. So these are just zero are one-layered models of deep learning. There is nothing in between. So one input layer of neurons, one output layer of neurons, and they themselves were able to make some reasonably good predictions. But how, unfortunately, the practitioners thought they created a real brain and hyped it, so it had to go through a natural death for some time, artificial death for some time, but then it was revived again. But you see, in 1950s, people have developed a one-layered simulator of a brain. But 1960s, they went out of fashion, though they solved some problems. Better models were created to solve such problems. 1980s, people developed math where they were able to put one layer in the middle. So brain has a billion layers, but in 1980s, we figured out how to do a 3-layered or a 4-layered structure of neurons, where each individual neuron does something very simple, but the way you connect them, some really complicated problems are solved. Another way to understand this is, I give the raw form of my input, which could be pixel, which could be word, which could be store ID, whatever that is, and the brain, artificial brain or artificial neural network actually learns better features. It is creating features in the second layer, which it is using to solve the problem. Though they just added one layer, the amount of or the range of problems that they were able to solve just shot up drastically. Just from no intermediate layer to one layer itself, again cheated the scientists that they were able to create an extremely powerful brain-like system. But the first generation autonomous self-driving cars had nothing but this, and they were able to drive miles and miles without any accidents. People solved some really exciting problems, audio, voice recognition. As I said, self-driving cars. The first generation versions were developed just with one intermediate layer. Now, 2005 onwards, and particularly in the past 4 or 5 years, our ability to build these deep neural nets has grown by leaps and bounds. The Microsoft net that I showed that beat a human accuracy in classification had 152 layers. So we really now know how to put as many layers as we want and create better and better and better features from the raw inputs and make predictions. So as a jargon, you can think of this as a simple or a linear model. Don't worry about the technical terms. This is a non-linear model, and this is a deeply non-linear model. So really, it is able to solve the problems that I showed in the motivation with the kind of accuracies that you are talking about. So the idea how a deep neural net works is, you are inspired by the brain. that great complicated models can be built by intelligently putting together multiple Lego blocks. So each block, or what they call a neuron, doesn't do anything outrageously smart. It just adds up things that come into it. It could be as simple as that, or it multiplies. It does something extremely simple, but the way you stack them, the way you connect them, really creates an enormous ability for the network to solve a variety of complicated problems. Now, so you probably now understand the first fundamental difference between deep learning and machine learning is I not only need not worry about the logic in deep learning, I don't even have to worry about creating the right kind of data. Raw data can be given, it will build like a brain. It is not brain. Nobody knows how brain works. So this is a machine that takes inputs that brain takes and gives outputs that brain gives, but the functioning is very different. And there are some theoretical proofs to show that it is very different. So let's not get carried away by the fact that we have created a brain. We have created a machine that can solve some problems that brain solves with an amazing accuracy, with the same input as what brain takes. Let's just stick to that definition. But deep learning doesn't need not only the logic, it does not need even the refined data. The raw form of data is good enough. The second major difference in a machine learning solution, typically what you notice is if you give the problem, if you give the model 100,000 records, let's say it gave you 90% accuracy. If you give it million, it may give you 92%. If you give it 10 million, it may give 92.005, or it may not even improve. After certain amount of data, that amount of data depends on the problem. In some it could be a few thousand, in some it could be a few hundreds of thousands, in some it could be a million. But after a finite amount of data, the performance doesn't go up. On the other hand, deep learning, as on today, there is no bounds to data hunger. So the more, the merrier. So as an organization practicing deep learning, you should start respecting data and have infrastructure to keep collecting data, as much of data as possible. And thanks to some of the hardware and software implementations, handling even billions of records is not too difficult nowadays. So second major difference, first one we already talked about, that we don't need the refined form of data. But the second major difference is there's no bound to the data hunger in deep learning. And another very interesting difference, and this I believe is the most exciting difference, is in machine learning, we have been trained to be extremely disciplined. So we as in the practitioners like me who probably practiced machine learning for 15 years, what we were told is take the data, create the right form of, to understand the problem, create the right form of data, pre-process it specific to that particular problem, build a model, use it in that particular problem. Now you want to solve a different problem, if it requires the same data also, you may have to completely pre-process it and use a different model. The ability to give portability to either the model or data is very limited in machine learning. On the other hand, in deep learning, we call this transfer learning. You take the data of one problem, use it to solve some other problem. Even better, you take the model you built to solve a problem like classifying images and use it to build a better recommender system or do better sentiment analysis. So data and models are cross-utilized, broken into parts, connected from rear end. People play with it. This is a heaven for engineers. I mean, just that Lego block setting is leading to phenomenal accuracies that you are seeing. So mostly engineers don't do the math of deep learning. Mostly in organizations, people are involved in building the right Lego block correctly so that the right answers are achieved. So that I think is going to revolutionize something that an MIT research lab developed yesterday to solve a problem in economics. I can take that and use more or less the same model with very limited training, with very limited data on my pharmacy system. And it works. So that way, this can get extremely collaborative and breathtakingly fast. And another important difference is in machine learning, we try to simulate the logic of solving a problem. So, hey, you know what? I believe I tell the system, I think the factors may have a linear relation with the impact, so or a non-linear relation. Can you try to model? So when I say linear, I'm talking about a straight line relation. The number of buyers will be equal to the amount of discount times M1 plus the duration for which the shop is open times M2, something like that. So I tell the system, hey, most likely this is the logic. I'm not sure, I'm vague about it, but can you build and quantify that logic? That's how I build a machine learning model. In deep learning, on the other hand, fascinatingly, we try to understand the process that brain follows. So let's say I want to talk about build a system that forecasts what I'm trying to say. This will be very useful when I'm trying to translate machine language, natural language. So I have a statement that says, I fell in love with this French girl. My family and folks were initially reluctant because of cultural differences, but they met her yesterday and they really loved her. They immediately said yes. All that is left now is to meet her parents and get their consent. So here I am booking my tickets to Dash. So a human brain immediately knows I'm most likely booking my ticket to somewhere in Paris or somewhere in France because I met a French girl. So, but how did I do that? Now, machine learning way is to actually design the logic. Hey, you know what? Probably I should look at all the countries that I used in the past 50 words. And probably I should see how many question marks are there at the end of the sentences, how many proverbs I used, how many pronouns I used. Now, I have to sit and write all these logic or factors that could influence. On the other hand, in deep learning, I think very differently. Hey, how do you think the human brain is tackling this problem? Amazing. How does it do that? Most likely, you know what? I have a gift to forget unimportant things. So I don't remember how many times I said "da" in the previous sentence, but I remember that I said French girl some 10 sentences back. So I forget some things and I keep learning a few things from every sentence that I read, and I know exactly what to extract from my memory to fill the next word. I just know that I have to extract that French connection and nothing else in between. So this is a process that consists of forgetting irrelevant things, learning relevant things, and extracting new things. A deep learning model, now they will build one model to forget, one model to learn, and one model to extract. So it is a lot more aligned and mapped to the way we humans think and process information. So it will be actually easier for us to understand why things are working. And well, there are some complexities on tweaking, etc., which I don't want to go through in such a short session, but it is actually easier to do that. But you see the fundamental difference. What I do in machine learning is try to hand code these extremely difficult logical factors. You know, how did I have a proper noun 5 words back, etc. Here, I understand the process and I simulate it. So it's a lot more architecturally elegant. So these are some of the fundamental differences. So it's not that a machine learning scientist automatically becomes a deep learning scientist. Architecting machine learning is same as architecting deep learning. You have to understand, you have to give a lot more data, you have to cross-utilize what you have done, and you have to build systems that architect processes and then connect those Lego blocks to solve a variety of problems. And just one quick slide to show that implementing has become easier than ever. The complexity of deep learning is not anymore implementation. Everything that you see on this slide, please don't worry about the technical terms, are all open source, developed in C or Python, downloadable, pre-trained, and a good engineer in less than 3 to 6 months will become an expert of implementation. I mean, a fresher. Depending on your skills in Python, it could be a week to a few months if you have to learn from the very basic Python. But this is not the complex part. What is complex part is what I was mentioning, the process understanding, the understanding of the differences between both approaches, and building the right set of systems. Those skills, interestingly, are not available anywhere in the system. Now that brings me to a very exciting part of this presentation. See, every reputed university is creating hundreds of deep learning engineers every year. We at INSOFE and Soothsayer create 900 deep learning engineers every year. So I don't think there will be a dearth of engineers who can implement deep learning. And as I showed you, breaking benchmarks is not going to be difficult either. So that is not going to be difficult. What will be difficult is for a CXO who has left the college and who is not going to code, full stop, who is not going to sit and code in Python, and that's not their job. What they need to understand is, hey, what can this do to my top line and bottom line, this new technology? And it is important because many people believe this is the electricity of this century. Organizations must learn to use them. And what new product solutions can I build with this thing? And how much impact will it have? What tools and frameworks should I use to analyze the impact of these products? And how do I democratize? If I build this product, how do I ensure that everyone in my organization uses it and their efficiency comes up? And what kind of talent should I hire? Is it enough if I go to an institute and hire 10 engineers, or do I need to do more than that? And most importantly, there will be these two groups that the organization will develop in every organization in the near future. A group that understands, and this will be a minority, the technology, and another group that expects them to wave a magic wand and solve every problem. This is causing real organizational friction. Every organization that we go to consult, one of the biggest problems that we find is the unreasonable expectations that non-practitioners have about deep learning and the difficulty that deep learning teams have to explain. As a decision maker and CXO, you need to understand these factors and then select mid-level management who can transform your dream into a reality, a product or a service. And that then requires a different breed of mid-level management, product managers and architects, who can leverage the right data and right model. They need to have an organizational view to pick the right data and right model that's already built to solve the problem. Design the right kind of error metrics. So how good is my model and how much of improvement really means a business difference? Netflix spent 3 years on building a model only to realize at the end that they cannot implement it. So as an architect or a product manager, I should know what exactly is the ROI and how much of improvement should I be looking at. In my experience, math never failed me in any consulting. If I ever faced a complexity or a failure, it's because this work was not done right. We either not using the correct model or not using the right error metric. And then at the same time, once we understand this as a practicing manager, we also as a practicing manager should develop the skills to guide actively a team of engineers. Help them undertake the right experimentations, analyze their model performance and ask them to do the right changes to build the right model. As I said, it is extremely easy to build a model, which means it's extremely difficult to figure out when it stops working. And that's where an architect steps in with the bunch of skills that are needed. In my experience, what I noticed is that these skills, the CXO skills and the architect skills that are lacking very heavily in the industry. And to address that, for those of you who liked what you heard until now and want to explore this further, I want to talk about two programs that we are offering in the next month. I will be personally offering this in Detroit and Columbus. The first one is a leadership seminar aimed at CXOs or senior managers, vice presidents who have to understand the P&L impact of deep learning. What we will cover there is the fundamentals of deep thinking that I outlined here. We will dive deeper, and we will also discuss frameworks and tools that you can use in deep strategies, what design thinking, what kind of agile methodologies and deep learning strategies that help you build a system fairly quickly and robustly. We are developing this in association with another mentor who is a researcher with Wharton Business School also. We are co-developing, myself and him. Then we will also cover a variety of use cases in a variety of industries to show you a link between what you could do in your industry. And of course, you will get a chance to network with peers from diverse industries to formulate fresh ideas. So this will be a one-day workshop aimed at managers who have to deal with the P&L. And then we have a 6-day program for mid-level managers who most likely have to lead a team to develop smart applications that the CXO has dreamt of. And these people have the responsibility to transforming it into a reality. So they will be given a bunch of engineers and they will be asked to build an application. So in this 6-day program, you will learn to architect a solution from end to end. We will work with you. So we have developed hundreds of lines of deep learning code that we use to solve real world problems on real data sets. We will help you analyze the code. The goal here need not always be writing the code, because we know majority of the participants may never have to code. So there's a lot of emphasis on reading and understanding the code. So we will work on a variety of data sets from variety of industries. You will analyze recommendations engines, text analytics, pattern recognition, fraud detection, demand forecasting, computer vision, how to build an application from ground up, how to guide teams. What are the typical pitfalls that people face while they are going through these kind of projects? What changes the duration from a few weeks to a few months or a few years and end up in failure? The real strategies that we developed and real technical tools and frameworks that we developed that help a leader lead a team actively to quickly build the system. So if, one of the questions that at the end, we actually give you in this particular 6-day program, there is a project that we will give you along with a business problem and some code, and you will be simulating the entire lifetime development of the product. So while this is optional, we strongly encourage our participants to take it. So this will be be, in my opinion, and in the opinion of people who have attended the program until now, this is perhaps the only such course designed exclusively for tech managers, product managers, and architects whose goal may not be developing the code. If they want to develop the code, of course, you will have hundreds of thousands of lines of code that you can redevelop. But more importantly, lead a technical team confidently and interface with a business team actively to build rapidly deep learning applications that can revolutionize your business. Here is the calendar. I won't read out the schedule, but at this point, I will be going through the chat box to see if there are any questions. Okay. When we cut apart human brains, we see either 5 or 6 levels, just so you know. Thanks, Ryan. Really, I don't know. What I know, however, is that the number of neurons in the brain are in billions, whereas we today in deep learning have a lot fewer, while it is much more compared to what we were able to do even 5 years back. To even today, we are talking about not more than a million or a couple of million neurons. But thanks for this information. Wonderful to know that.
This is Gaurav from Soothsayer. If anyone have any other questions, please type in the chat window. And if you would like to get a copy of the presentation, please send an email to ian@soothsayeranalytics.com, having your email ID, phone number, and full name, and we'll be happy to share that information with you guys.
Yeah.
Any other questions before we wrap up for today? And just that you guys know, we will have another session in the upcoming week within the next 10 days. If you are interested, you can stay in touch with us, with Ian, Devin, or Chris, and we'll be more than happy to share that information with you. Yeah.
Ryan, will there be, there's a question that says, will there be later sessions? We haven't designed the calendar yet, but yes, we will have the session at a later point, but not in this quarter, definitely. Sheen, Gaurav, the question is, will the recording be available at some point? I guess it will be. Please share your email ID. And we will come back to you on that.
Yeah, so Jeff, you can stay in touch with us and we can work with you to provide that information. And Ryan, we will have more sessions coming up in Columbus, Detroit, and also we are having a session in Cleveland, along with Case Western University, which is happening in March. So yes, we will keep you guys posted about it.
If there are no further questions, we can end the session here. But Gaurav, I'm good from my end. Okay. I'm done.
Yeah, thank you so much for attending this webinar. As I said, we will keep you posted about the further webinars and further sessions that we will have in data analytics, deep learning, artificial intelligence, and related topics. Thank you so much to everyone, and have a good day.
Thank you very much. And if possible, have a warm day. I know it's probably asking for too much, but thank you very much for attending.
Thank you, Dr. Murthy.
Thank you. Bye.